Hello everyone, this is Dr. Lei Zhang from the University of Maryland Eastern Shore. Today, I want to share you our experience in offering a basic circuit lab. In this lab, we introduce the basic concept of pulse width modulation. More important, the using of analog discovery kit is integrated in offering this lab. By this way, the teaching effectiveness can be significantly improved. Basically, pulse width modulation is a technique for getting analog results, especially voltages, with digital means. Digital control is used to create a square wave by switching constant inputs between on and off. As can be seen from this figure, by modifying the width of pulse signal, output voltages with different average voltages can be acquired. The system diagram of this experiment is shown in this figure. The DC motor is connected to the battery through the driver chip to get the power supply. The driver chip is controlled by the Arduino. The Arduino will generate the pulse width modulation control signal to control the driver chip to distribute the power to control the motor speed. Components needed in this experiment including the following. The first is the analog discovery kit, and the second is the microprocessor Arduino Uno. The third one is the dual motor driver carrier. The last one is a micro metal gear motor. A key component of this experiment is the analog discovery kit. The analog discovery kit is a mobile laboratory kit that can drive, measure, and visualize for both analog and digital signals. It can work as all major laboratory instruments, including the multimeter, function generator, DC power supply, and oscilloscope. Arduino is a very well-known and very popular entry-level microprocessor. More specifically, the Arduino Uno is an 8-bit microcontroller board based on the CPU of AT-MEGA328. It has 14 digital input-out pins, in which 6 can be used for the PWM purpose. They are pins 3, 5, 6, 9, 10, and 11. It also has 6 analog inputs, a 16 MHz resonator, and a USB connection. In Arduino, pulse width modulation digital control is used to create a square wave in which a signal switched between on and off. This on-off pattern can simulate voltages in between full on, which means 5 volts, and off, which means 0 volts. By changing the portion of the time the signal spans on versus the time that the signal spans off. To get varying analog values, the pulse width can be changed. The layout of the motor driver chip is shown in this figure. The basic function of this chip is to drive and control two motors separately. The two PWM control signals are to be connected to the two pins PWM-A and the PWM-B on the right side. This figure shows how to wire between two motors, the driver chip, and Arduino. The two connectors on the bottom, motor power, are to be connected to the battery to supply the power. This figure shows the circuit setup of this experiment. A ground roller chassis is used to demonstrate the speed change of the DC motors. A 9 volts battery is used to drive the Arduino. 4 AA batteries are used to drive the two DC motors. On the up left corner is the analog discovery kit. It is used to measure and visualize different signals. This figure shows the programming interface of the Arduino. It can be seen from the beginning of the code. First, the P9 is selected to be the PWMA, which is used to generate the pulse width modulation signal to control the speed of motor A. In the second line, at the first, the speed is set to be 25. The PWM signal is an 8-bit signal, so on maximum, its value can be 255. And then correspondingly, 25 is about 10% of the maximum value, which means the duty cycle is about 10%. By the use of the analog discovery kit, the pulse width modulation signal generated from an Arduino pin can be visualized as shown in this figure. It can be seen here, as we mentioned in the last slide, that when the speed is set to be 25, the PWM signal generated has the duty cycle about 10%. Then let's modify the speed parameter to change it from 25 to 125. Compared to 256, which is the maximum value, here 125 is corresponding to about 50% of the duty cycle. It can be seen from this figure. After changing the speed parameter from 25 to 125, the pulse width is also changed from the original 10% to about 50%. By setting the speed value to different numbers between 0 and 255, different pulse widths can be generated from the pin on Arduino, and then to control the speed of the motor on ground roller. In this experiment, students are expected to learn the basic concept of the pulse width modulation, to build the circuit, to assemble the ground roller, and the program to change the speed by the use of pulse width modulation. At the end of the experiment, students will be asked questions about the basic theory of this pulse width modulation and also the devices and components used in this experiment. By offering this lab to our students, we integrated the experiential learning approach into our teaching practice. Meanwhile, we also want to evaluate the effectiveness of this experiential learning approach. Shortly, from the feedback and discussion after the experiment, we have confirmed that this experiential learning approach can greatly improve our students' learning experience.